This is the presentation for our ICRA 2021 paper, Avoidance Critical Probabilistic Roadmaps for Motion Planning in Dynamic Environments, which is a collaboration between Felipe Felix Arias and Nancy Yamamoto from the University of Illinois at Urbana-Champaign, and Brian Ichter and Alexander Faust from Google Brain. In this talk, I will present our work on multi-agent navigation and motion planning, where the primary goal is to efficiently compute paths that take planar agents like mobile bases and humans to their goal destinations and avoid collisions with static obstacles and other agents. Here we have a simple example of one of the canonical interactions between two agents in an office-like setting. At the center of the frame is a narrow passage that both agents need to traverse to get to their goals. However, it is only big enough for one of them, so one of the agents must wait for the passage to clear. The agent engaged in obstacle avoidance must pick a location to wait for time to pass, but there are multiple roughly equivalent solutions in configuration space. Here we show two valid solutions, but there are countless less appropriate ones, where the agent may avoid a collision but hinder the navigation of the other. Our contributions focus on sampling-based motion planning methods, which reduce motion planning to pathfinding by sampling and connecting samples to make a graph representing the possible states a robot may move to. Here we have some images of sampling-based methods at work. The circles in the first two images are samples, and some of them make up the path the robot will take to get to its goal configuration. The methods shown here bias sampling to get connections in narrow passages. Rather than sample uniformly, they sample in regions that are likely to be a part of the solution trajectory, which improves performance in environments of narrow passages. In the multi-agent setting, which in our case simply means that a roadmap is used by two or more agents simultaneously, the search space grows exponentially in the number of agents. This leads to pathfinding being the bottleneck and the need for sparse roadmaps that have a good coverage and reduce blocking. With this in mind, other multi-agent motion planning methods use standard sampling techniques that do not account for workspace topology or obstacle avoidance, with grid sampling being the most prevalent, since a grid discretization is the simplest method that can be used to find solutions in the planar setting. As I mentioned, roboticists seek to identify relevant regions to improve sampling efficiency. This is in big part due to the fact that in practice, solution trajectories only rely on a few critical states. Many methods bias sampling near obstacles, narrow passages, or towards optimal trajectories. Notably, critical probabilistic roadmaps, or critical PRMs, which were proposed by some of us in ICRA 2020, use neural networks to identify relevant regions from local features. The self-supervised procedure works by building many dense roadmaps in multiple environments and using betweenness centrality, a measure of how frequently a vertex is visited in the shortest paths through a graph, as a score for criticality. The inputs to identify critical samples are local topology representations, and the critical samples identified by the network are leveraged above uniform samples when constructing a critical PRM. The method I am presenting today is called Avoidance Critical Probabilistic Roadmap, or ACPRM. These roadmaps enable efficient obstacle avoidance, reduce the search space, and increase a roadmap's coverage and reusability. Therefore, we focus on path length, sample complexity, planning time, and roadmap construction time of sampling-based methods. Here we have two images, one that shows a roadmap built using grid sampling, and an ACPRM which uses 3 times fewer samples. Naturally, we are interested in identifying relevant regions in dynamic environments. To the best of our knowledge, no other methods propose a heuristic for desirable locations. Cruz et al. Note that there has been extensive work on cost functions and affordances, which are regions to avoid. As shown in these images, some of these are regions near humans or in a human's way, but agents may also want to avoid taking tight turns to avoid collisions, as shown in Figure B. The goal is to identify regions of workspace critical to navigation in dynamic environments. However, that is a very broad concept that we are only starting to explore. Instead, we have the objective of identifying regions of workspace critical to obstacle avoidance. The problem then becomes one of finding a methodology for learning to identify such regions. ACPRMs use a self-supervised model that is trained by solving a large number of navigation problems in dynamic environments. We use waiting in place as a cue for obstacle avoidance, as it only occurs when finding optimal trajectories in dynamic environments. By keeping track of how frequently a region was used by agents for obstacle avoidance, we can generate a training label for a neural network that takes in occupancy grids. In the first image, we show what these regions look like in an environment annotated with 236 random navigation tasks. In the bottom, we highlight the regions our model found to be critical using a sliding window procedure. The heuristic learned consists primarily of regions surrounding entrances and junctions of narrow passages. But we note that many variables may determine what avoidance criticality looks like. The number and types of obstacles, planning algorithms used, and environments determine what avoidance criticality looks like in a specific scenario. In our case, we choose to introduce one obstacle that takes the shortest path from the goal to the start of the agent's task, and one with a random path. Our environments are randomly generated but consist of hallways and rooms, which gives us a heuristic for this specific topology. For data generation and all of our planning, we use Safe Interval Path Planning by Phillips et al., which may be used as a decentralized multi-agent pathfinding algorithm. To train our model, we compiled a dataset of 140,000 11 by 11 occupancy grids from 450 randomly generated environments. Since we are working in the binary classification setting, we balance our training data so that half of our occupancy grids are critical and use avoidance criticality to train a fully connected neural network. Here we have some critical samples from our training data. The region at the center is where an agent may wait in place in a dynamic environment. Before presenting the ACPRM algorithm, it is important to note that we are only discussing one instance of how spatial contextual awareness may be used for dynamic environment navigation. Here, we use avoidance criticality and occupancy grids to build roadmaps, but navigation also provides data such as proximity to other agents and semantic cues, which may be just as important for criticality. The goal is to enable agents to reason about their surroundings. For example, an agent's intent may determine criticality. In this example from our dataset, the agent starts in the green dot and wants to go to the red dot. When entering the narrow passage, the agent may need to avoid a collision with an agent going in the opposite direction, making the critical region at the center a good cubbyhole to wait for the passage to clear. However, an occupancy grid with roughly the same topology, marked with an X, is not critical given the agent's intent. It is only visited when exiting the narrow passage, and therefore, the likelihood that the agent will have to wait there is small. ACPRMs are roadmaps that are built in two stages. First, the binary classification model we introduced is used to identify relevant regions using a sliding window procedure. We then sample in these regions and connect our samples to one another using a large connection distance. After building a skeleton, we propose to use a uniform sampling strategy to finish the problem, though any sampling strategy may be used. Once you have a roadmap that connects all of the starts and goals, a pathfinding algorithm finds valid paths for all agents. Here, the image on the top is an ACPRM, while the bottom shows what the sampling would look like if we did not connect the critical samples first. We have a couple of experiments that show some of the main features of ACPRMs. First, we show that our method can be used to find solutions in environments obtained from real-world 3D scans. The sparse roadmap on the left is an ACPRM, and it finds solutions for 8 agents 2 times faster than grid sampling, shown in the right. As can be seen, grid sampling, or a grid discretization of the environment, results in 3 times more states, but equivalent paths in terms of path length. The second set of experiments in small environments shows an ACPRM growing to accommodate 1, 4, and lastly 8 agents. On the left, the critical samples are clearly visible, clustered at the center and surrounding entrances to narrow passages. As more agents are introduced, the figures show how ACPRMs increase in size to find solutions for all agents, keeping the roadmap sparse. The plots comparing the performance of an ACPRM and the grid sampling baseline show the runtime, number of samples, and path costs as the number of agents increases. For all of our experiments, an agent starts at a random room and has to move to another randomly assigned room. ACPRM is up to 5 times faster than grid sampling for 8 agents. As the number of agents increases, the planning time increases. Since ACPRMs have far fewer samples, as shown in the second plot, they find solutions much faster while resulting in only slightly longer paths, as seen in the third plot. Since the performance is much more competitive when there are fewer agents, these plots show that pathfinding is the bottleneck for grid sampling roadmaps. In our last experiment, we showed that ACPRMs are able to scale to large environments and find solutions to problems that are not feasible for grid sampling. Since our baselines cannot find solutions sufficiently fast, we compare our method against the others in the multi-query setting. While an ACPRM can support up to 15 agents moving simultaneously, grid sampling and medial access PRM take longer to simply build a roadmap that connects all starts and goals. The runtime of ACPRM shown on the left is up to 10 times faster than medial access PRM, a competitive method for large environments with narrow passages shown on the right. And we can also see that it constructs the roadmap up to 2 times faster than grid sampling. When solving the multi-agent motion planning problem, the performance of the ACPRM is proportional to the number of agents as shown on the left. After 10 agents, the runtime begins to increase over the multi-query setting, because more states need to be explored to find collision-free solutions. Overall, ACPRMs are shown to be faster and produce paths as short as those found using grid sampling. Moreover, the ACPRM is the only sparse enough roadmap to support multi-agent motion planning. Lastly, I would like to reiterate the main points of this talk. We introduced a self-supervised methodology for training a model to identify regions relevant to obstacle avoidance. ACPRMs, which leverage such models, can help construct roadmaps that enable efficient obstacle avoidance, reduce the search and planning space, and increase a roadmap's reusability and coverage. Most importantly, we hope that this project is the first step towards enabling robots to prevent encounters with obstacles, irrespective of their trajectories, by being conscious of spatial context cues such as the location of choke points and obstacle avoidance. Thank you for watching. Please visit our website for more information.